Hello, students. Welcome to the first video session on circular motion. The aim of the video is just to introduce the learner to the concepts and terms used in circular motion, and then later on describe how these terms relate to those encountered under linear motion. So the video is just basically a general introduction to what circular motion is. It doesn't really go on to look at complicated concepts like torque or a moment of inertia or angular momentum, but it kind of creates a foundation for such concepts. So we're just going to look at terms like angular velocity, angular momentum. So I won't really reach angular momentum in the video. We'll look at angular velocity, also angular acceleration. We'll end by looking at centripetal force as well. Then we're also going to work out a number of examples, some of them coming from exam past papers. Okay, so to start, the time we looked at, in your study of linear motion, the first thing that you had to do was to describe how an object moving in a straight line, more like how to determine its displacement. That's the first thing. So you see, in circular motion as well, we have to also look at what the displacement is. But unlike in linear motion, where objects are moving in a straight path, here objects are moving in a circular path. So if we're going to describe the position of an object at any point along its path, then we have to do it in terms of angular displacement. Now let's take a circle of radius r, and then we want to track a point P, which is moving along the circumference of this circle. To track its displacement at any point, we have to specify its angle along, it's the angle it actually moves as it covers some arc length, let's say L. So let's say this point P move from this point to somewhere here, and then in the process it makes an angle, or it undergoes displacement, angular displacement of theta. Then to specify its displacement, what we're saying is, in circular motion, all we have to do is to state what this angle is. Now there is a way of calculating this angle given the arc length L and the radius r. So here we're saying the angle, the angular displacement is given by the arc length divided by the radius of the circle. So this simple equation can be used to determine the angular displacement theta. Or can we write it in terms of L, when I was saying the arc length L is equal to the radius times the angular displacement. Now, since this is in circular motion, we're going to work a lot with angles. But then for conveniency, when dealing with circular motion, it is always preferred to work with the radians instead of the degrees that we've been using in most cases. Now, this makes it important for us to know how to make the conversion from degrees to radians, or from revolutions to radians as well, and vice versa. Now, how do we do that? So if the point P was to move from the original position all the way and back to this position, in terms of degrees, the angle covered is going to be 360. But in terms of displacement, in terms of arc length, the total circumference of the circle that would have covered, of course, is just going to be 2 pi r, which is the circumference of the circle. So L in this case is going to be 2 pi r. R remains as the radius, so we're just going to substitute that. So if we come back to our formula here, we want to see what the angle will be for the full rotation. So in terms of degrees, the angle is, I'm using the equation now, this equation. In terms of degrees, it's going to be 360 degrees. Now, in this case, in terms of arc length, we're talking about 2 pi r. So the right-hand side is in radians over radius r. So this cancels with that. So the answer, of course, is in this part. So now we then use this relation to say 360 degrees is actually equivalent to 2 pi in rad. So this is what we'll always use when we want to convert. Now again, if you look at this full rotation, so you can say this is one rotation, or you can also say this is one revolution. So now what we're saying is one revolution, abbreviated as a rev, is equal to a 360 degree turn or rotation, which is also the same as just the 2 pi radians. So I can use this to make whatever conversion that we have to deal with, whether from radians to degrees or from revolution to radians. Depending on what we have, we can use a pair of this. Okay. All right. So the rad here is just short for radians, of course. So it's just short for this name, radians or radian. Okay. Now let's look at a simple example just to see what this means. So in this example, we're talking about a bike wheel that rotates 9 revolutions. And then the question is, how many radians is this? So we want to convert 9 revolution into rad. So now, having looked at the conversion factor, so since it's revolution going into radians, so I'm going to say, I'm going to use this part. 1 rev is equivalent to 2 pi in rad. Okay, so this is what I'm going to use. So here I'm just going to multiply. Since the rev is in the numerator here, so I'll have this part in the denominator. So this becomes 1 rev, and then this becomes the numerator, 2 pi rad. So this cancels with that. Then now I'm just multiplying 2 pi by 9. So just multiplying 2 pi times 9. And then whatever I get, notice the unit that remains here is just the rad. So if I perform this multiplication, so I have 2 pi times 9. I get 56.5. So here we get 56.5. 56.5 in rad. Okay. So this was just very basic and straightforward. Let's look at something else. Okay, so in this example now, we're talking about a particular bed, what it can see, and so on. So if you can try out the question, just pause the video and try. It's just very simple. The first one, they're asking us to convert an angle given in radians to degrees. And the second one, they're trying to, they want us to determine the smallest size an object in this bed can actually see. Okay, now let's start with the first one. So the angle is given to us in radians. So this is given somewhere here. That's 3 by 10 to the power negative 4, right? They want us to convert this to degrees. So here we're going to multiply. So again, the conversion factor. So if you recall, we had the degrees to radians. It was 360 degrees equals to 2 pi rad. So I want to eliminate the rad, so I'm going to have it in the denominator. So I'm going to have 2 pi rad, and then the numerator I'm going to have 360 degrees. Okay, so when you're dealing with the degrees and the radians, of course, you can easily divide the two here. It goes there, so that this, you can use it also as 180 over pi. Right, this also works. This also works. So it's just up to you. Okay. Right. So after having this, you notice the rad cancels out. Let's see what remains. If we work out what remains, divide, multiply. You notice that the answer we have comes to give us 0.017 degrees. Okay, the next part now, they want us to find how small an object this bird can see, this bird can distinguish. So we just have to create a picture of what the question is actually saying. So let's say the bird is somewhere here. The question specifies that it is at a height 100 meters. So from the ground, this bird is all the way up to 100 meters. Okay, now the same. So it can distinguish, so in this part the same, particular bits I can distinguish objects that subtend an angle no smaller than 3 by 10 to the power negative 4. So if you had an object that was here, so the bed will be able to distinguish what this object is if the angle that this object makes is not smaller than the 3 by 10 to the power negative 4. If it was smaller, the bed will not be able to distinguish. But if it is at least that it makes that angle or something bigger, then the bed will be able to see it. So to work out this, we'll treat this as we'll treat the size of this object as an arc length. So treat this size as an arc length, then the 100 meters becomes somewhere here. So if you recall, this then the relationship becomes this becomes the radius, that becomes the angle, this becomes the L. So we'll use this part. Angle is equals to the arc length divided by the radius, or arc length is equals to the radius times the angle. So in this case, the radius is given as 100 meters. The angle is given as 3 by 10 to the power negative 4. So if we multiply this, what we get is 3 by 10 to the power negative 2 meters, or this is can be written as 3 centimeters. Okay. All right, so this is just basic conversion really, so shouldn't give you that much of a problem. Now let's start looking at our terms. So the first thing that we're going to describe here is angular velocity. Now one thing I have to specify here is when it comes to these terms, the way we treat them is similar to the way we treated similar terms in linear motion. So in linear motion, we did see that velocity was defined as the change in displacement over time. So in this case, we're using L for displacement. So we're saying it's not really the change. We just said the displacement over time. So if we're looking at angular velocity, so the same thing can be said for angular velocity. The symbol we use is omega. Now its definition, what we're going to have is omega, which is angular velocity, is equals to the displacement here as well over time. But instead of L for displacement, in terms of angular velocity, the angular displacement we're going to have is the angle. So it's the angular displacement over time. So, but sometimes this angle, you have to know that it's the change in the angle. So if the angle changes from 30 to 40 degrees, then the change in angle has to be respectful one, but of course not in degrees. We'll use radians strictly. Okay, so it's the change in the angle over time, or let's say the change in the angle over the change in time. That gives you the angular velocity. Now, of course, this can also be written as the final angle minus the initial angle over the change in time. Okay, so that is for angular velocity. Now, when it comes to the relationship between angular velocity and linear velocity, all we have to do is start from here. You see, for velocity, angular in a straight line, so we say tangential velocity. What happens is, of course, the original definition, we're looking at the displacement over time. But in terms of displacement, we saw earlier on to say that this displacement in terms of length, in terms of L, is just given as LR. So if we substitute this there, then this becomes the change in R, that over the change in T. And then the radius is a constant, so we can factor it out. This becomes the change in theta over the change in time. So you notice that this term is exactly what we had for angular velocity, implying that we can conclude that the tangential velocity or the linear velocity is related to the angular velocity in this manner. So this then creates the relationship between tangential velocity or linear velocity to the angular velocity. Okay. Now, let's quickly look at at angular acceleration. So when it comes to angular acceleration, the symbol we're going to use is alpha. So in this case, just as we saw for angular velocity, the relationship as well is very striking. For linear acceleration, we had this is equals to the change in velocity. And this is all tangential or linear over the change in time. So the same thing will apply for angular acceleration. Angular acceleration is defined as the change in angular velocity this time over the change in time. So the angular velocity, of course, you just have to recall, this is going to be the final velocity minus the initial velocity over the change in time. Okay, so this simple equation gives you the angular acceleration. But to relate angular acceleration to tangential acceleration or linear acceleration, we're going to get back to linear acceleration. So for linear acceleration, in this case, we use a t to mean acceleration at a tangent. The tangent, of course, is a line which touches the circle at only one point. So where we have vt here, so let me just bring that down for now. Vt over change in t. So again, we recall the time we are working out the tangential velocity. We concluded that it relates to the angular one in that case, with that equation. So we're going to substitute that where we have vt. So this becomes r omega. So just substitute vt and its expression there over change in t. Radius again is a constant. I factor it out. This then becomes r change in omega over change in t. So again, change in omega over change in t, when we check here, this is just the definition of angular acceleration. So then we come up with this relationship, r alpha. So this is how angular acceleration relates to the tangential acceleration. Now at this point, I have to mention one thing. The equations, everything we did in linear motion applies to angular in angular motion as well, or in circular motion. So the three equations we had in linear motion, that was v is equals to u plus at. In terms of circular motion, the v here becomes the angular velocity. So this becomes final minus this is initial. So this is going to be omega initial plus the acceleration is now angular acceleration. So this becomes this. And then where we had s is equals to ut plus half at squared. The displacement s here. Now, again, you have to remember the first thing that we described in this unit. So the displacement in terms of angular motion is given in terms of the angle. So now we have theta is equals to the initial velocity, which is omega I, multiplying the time, plus half the angular acceleration, the time squared. And then the last one, which was v squared, u squared plus 2as becomes omega final squared, omega initial squared, plus 2 alpha theta. So this is the relationship. Basically, it's just the same. It's the change of units, the change of variables that we have to look at. But the equations still hold. Okay. So having described this, let's see if we can work out a few examples. Okay. So let's start with this one. So we have a carousel is initially at rest. So if you're thinking about what a carousel is, just think about it in terms of a merry-go-round. So a carousel initially at rest. So if they say initially at rest, they are saying initial velocity, since we're in circular motion, I'll use the symbol for circular motion. So it's initially at rest at t is equals to 0. It is given a constant angular acceleration. So they're giving us what the angular acceleration is, 0.08. Now notice the units. This is rads per second squared. What are we saying rads? For acceleration, we had the change in velocity, angular velocity. And angular velocity came in rads per second. So this was in rads per second. And then it's going to divide with second the time. So it's going to become rads per second squared. Again, not a similarity to what we had in linear motion. In linear motion, it was meters per second squared. Now it is rad, which is the unit of the displacement in angular motion. Okay. So now the next part, which increases its angular velocity for 10 seconds. So time changes from 0 to 10. So the change in t here just becomes a 10 seconds. Now they want us to determine at this particular time the angular velocity and then the linear velocity of a child located 3 meters. Okay, now let's start with the first one, the angular velocity. So given the initial velocity, the acceleration, and the change in time, notice that here we can just use the equation which was this in linear motion. But now we're saying this is final is equals to omega initial plus alpha t. So want to find the final velocity after 10 seconds. The initial is 0 plus the angular acceleration is given to us as 0.08. The time here is 10 seconds. So when you multiply, we get this as 0.8. But since this is velocity, this is rad per second. Okay, so this was quite straightforward, really. So then we look at the next one. So for the next one now, what they're saying is we have a child who is seated somewhere on this particular carousel. So this child is at a distance from the center of this carousel. So now what they want us to find is his linear velocity. So if you think about it, for P, we have something like this. This child is at a distance r, let's say this is given as 3 meters. And then they want us to find his tangential velocity, having found his angular velocity. So his tangential velocity just relates. We saw how it relates to that. So the tangential velocity is given as the radius multiplying the angular velocity. So what we should see directly from here is that if we multiply the radius by the angular velocity, what we get is going to be the tangential velocity. So we have 0.8 by 3, and we get 2.4 meters per second. Okay. Let's quickly look at another example. So I found this this question in a past exam paper. It was an exam paper. I thought it would be interesting for us to look at. So we're talking about a motor which takes 8 seconds to go from 60 rads to 140 rads at a constant angular acceleration. The total angle through which its shaft turns during this time is. So you can try it. You can try to pause the video and try to see if you can work this question out. Okay. Right. Let's see how you can work it out. So in this case, we start with the basic definition of what acceleration is. So acceleration is, of course, obtained by multiplying. In terms of, let's just deal with angular symbols. Final minus omega initial over t. So the final velocity is given to us as 140 minus the initial velocity is given to us as 60 over the time. The time is 8 seconds. Okay. So if we work out this, so we have 140 minus 60 divided by 8. So you get 10. So the angular acceleration is given to us as 10 rad per second squared. Okay. Now the next part here. So we're going to move on to look at another equation. So this time around, we're going to use omega final squared is equals to omega initial squared plus 2 okay. Okay, so yeah, so here we have 2 alpha, but instead of displacement S, again, remember, for displacement, we're using theta. Okay, so now this is the angle that we want to find. So the omega final, this is 140 squared is equals to, this is 60 squared plus 2 multiplying 10 times alpha. So this becomes 140 squared. So that's 140 by 140. We get 19600. And then 60 squared, we have 60 squared, we get 3600 plus 20 baht. Okay, so again, don't forget, I got the 10 from this calculation. So we got the angular acceleration first. So this is the one I've substituted here to, as my acceleration. So I want to get the angle here. So this moves to the other side. Now I have 19600 minus 3600 is equals to 20. That, and then I subtract. So that's 19600 minus 3600. I get 16,000 is equals to 20 angle. Divide both sides by 20 over 20 over 20. So now I have my answer here divided by 20 and I get 800. So this gives our angle that as 800. So this is an angle. So this is right. Okay. So when you go back to our question, this becomes the final answer. All right, so I hope you were able to follow through what was happening. Okay, so let's quickly move on to the next part. Let's quickly move on to the next part. So having described what angular acceleration and angular velocity is, now there's just one thing I want to quickly mention. When it comes to circular motion, the total linear acceleration a point in a rotating object has, it is going to be a vector sum of 2 components. So whatever the acceleration an object experiences in a circular path is going to be a sum of 2 components. These components, it's going to be the first one, we've already seen what it is, the tangential acceleration. Plus, the second one is going to be the radial acceleration. Now, this radial acceleration, sometimes it is given, or we mostly talk about it in terms of the centripetal acceleration. So what this means is if you have an object that is moving in a circular path, if you have an object that is moving in a circular path, it will experience an acceleration which kind of draws it towards the center. Okay. So it experiences an acceleration which takes it in this direction. This is the acceleration we're calling the centripetal acceleration. But then we've just seen that it also experiences an acceleration at a tangent. This is the one I'm calling the tangential acceleration. So the vector sum of these two, the combination of these two vectors, this is what gives us the total acceleration that a body moving in a circular path will experience. Now, we've already seen how to get this given the angular velocities and how they're changing. Now, in terms of the centripetal acceleration, the formula for that is basically just the tangential velocity squared divided by the radius. Now, once you know what the centripetal acceleration is, this leads us to an interesting term. We're going to spend a lot of time here, which is called the centripetal force, FC. Centripetal force. Now, this force, centripetal force, of course, from Newton's second law, it's supposed to be force times ma, but the acceleration is in the direction of the force, so centripetal as well. But since we already know what the centripetal acceleration is, we substitute that here, then we have vt squared over r. But earlier on, we did see that Vt is just r omega. So when you substitute this here, the same equation can also be written as m r squared omega squared over r. When r divides with that, this can be written as m r omega squared. So this can be given as the equation for centripetal force, or you can use this one as well. So depending on what you're given, these equations can depends. Yeah, you can literally up to you. Okay. Now I could have left this part for the next video, but I thought of including it so that when I say you try this question out later on, you have enough tools to work it out. So this question kind of interesting. I found it in a number of exam papers. Of course, values changing here and there. But in this exam, it carried 11 marks. I found it in the 2012, 2013 final exam. So just try it out and see what you can what you will find. But all the things that that are here, they are everything that you need here. You've already learned them. Some of them just in this video share the concept about centripetal force. But most of the other things you've looked at them in the previous topics that you've done. So try it out. If you want to see what I will find, then subscribe to the channel so that next time when I upload a video, you won't miss it. The concepts on how to work this one out will come in the next video. So yeah, I think this is as far as we'll go. The video has already been long enough. The other videos, the next one of course will be the solution to this and a few other examples. And then after that, we're going to continue with a description of circular motion. We're going to look at things like inertia, moment of inertia. We're going to look at angle. We're going to also introduce angular momentum. So yeah, I hope you found this video interesting. If you did, if it was helpful to you, just subscribe to the channel. And drop a like. Yeah, night. Thank you very much.